Hello all, in this lesson we're going to be studying work and energy, and this is our first lesson in Unit 3. The homework associated with this lesson is 1 through 25 on pages 83 to 84. And the aim that I want you guys to copy down for your classwork page is how is work related to energy and power. Then we have this 2 now that I want you to copy down, which we'll answer in class when I see you. All right, work and energy. So energy is the ability to do work, and of course it's scalar because there's no direction associated with energy. Perhaps more interesting than energy at this early stage in the game is the concept of work. And work is when you transfer energy from one object to another, and the object must move. So there's no way around that. If you push and push and push on the wall, and the wall doesn't move, then you haven't done any work. I know that sounds crazy, but in physics, that's the truth. The force can be in the direction of the object's motion, or it could have components in more than one direction, so trigonometry will be involved here. And whenever you do work on an object, you are changing its total energy in some way. The equation that we use to describe work usually is pretty simple. It usually is just work is force times distance. So you can see that you have to apply a force and the object has to move. But if you have a force and a distance, then you can find work. A lot of this you may remember from earlier in the year, but the unit for work and energy are the same, which might make some sense now since work and energy are so related. But it's joules. And of course, the unit for force is Newton, and the unit for distance is meter, which means that 2 equivalent units are the joule and the Newton meter. I also think it's helpful to remember some dimensional analysis techniques with work. So work is force times distance, and force is ma. So that just means that you could, instead of using FD, there are examples of questions where you might use MAD instead of FD. So keep that in mind, that force can be substituted for mass and acceleration. So here's a question. When a student applies a 50 Newton force horizontally against a wall for 60 seconds, how much work is done on the wall? And why do you say that? So I would say that no work is done on the wall, and I would just write 0 joules. And the reason that I say that is because the wall doesn't move. And work, of course, includes distance. So if the object doesn't move, then no work has been done. I have another question. When a student holds a 100 Newton block in the air for 5 minutes, how much work is done on the block and why? So again, I would say 0 joules of work is done on the block, and the reason is because you're holding the block in the air and it doesn't move. Okay, so here's a region-style sample problem. We have a 2.3 kilogram block at rest on a horizontal surface, and there is a constant force with a magnitude of 5 newtons that's being applied to the block at an angle of 30 degrees to the horizontal. So we want to calculate the work done in moving the block 2 meters to the right. So I want to know the work that's done in moving the block this way, which you may understand is not the same as asking for the work that's going to be done along this direction. So the general idea here is that there are 5 newtons of force being directed up into the air, but it's going to be less than 5 newtons that are directed to the right. So we'll use a bit of trigonometry to figure out what component of that 5 Newton force is horizontal and to the right. I suggest using the equation AX is A cosine theta, where AX is the horizontal component of the force. A is the hypotenuse or the resultant force, so I'll put 5 in for that. And then we're going to need the cosine function with an angle of 30 degrees. So this isn't the answer yet, but I was able to find that there are 4.33 newtons out of that 5 Newton resultant, which are directed to the right. And from here, we can just use our equation W is Fd, And now that I know that there are 4.33 newtons directed to the right, I just need to multiply it by a distance. And it does say that the block is moving 2 meters. So when I do 4.33 times 2, I got 8.66, and with significant figures, you could just write 8.7 joules. All right, so we also have in this unit this concept called power, and power is similar to work and energy as well. But one major difference between power and work is that power also depends on time. So one example I often use to explain the difference between power and work is that of you and your friend going up the stairs on your way to class. So basically, if you and your friend both climb 6 flights of stairs, assuming you have the same mass, then you will have done the same amount of work, because you'll be moving the same weight over the same distance, because you're climbing to the same height. However, if you and your friend climb those stairs at different rates, let's say that one of you climbs the stairs slowly and the other one climbs the stairs quickly, then you'll probably notice that those two things feel very different. And the reason for the difference in the way those two things feel is because climbing the stairs quickly is doing the same amount of work in a shorter amount of time, and therefore you're expending more power. So, the person who climbs the stairs slowly is going to be expending less power. So power is a time-dependent function, and the more work you do in the shorter amount of time, the more power has been dissipated or expended. The unit for power is called a watt. And it is defined as a 1 joule per second. The equation for power is, at least one of them is pretty simple. It's just defined as, so this is P, power. It's defined as an amount of work done in a given amount of time. The work is going to need to be in joules, and time is going to need to be in seconds. But remember, work is also force times distance. So you have another equation which could be force times distance over time, just knowing that force times distance is equal to work. And then lastly, we have distance over time right here, and distance over time is actually average speed. So you could do force times average speed, and that would also give you power. All of these equations are on your reference table. They'll look just like this, and I believe they're on the back page towards the bottom. And I would also just like to add that this W stands in for work, but we also have the unit for power, which is watts. And the symbol for watts is also W. So just don't confuse the italicized W, which is the quantity of work, with non-italicized W, which is the unit watt. And I'll make a note about this now. I think that with a little bit of reading comprehension, you won't have any confusion at all, but it is just a note of something to pay attention to, because it could be confusing if you were working too quickly or not paying attention. So because power is inversely proportional to time, based on the equation P is W over T, so since power is inversely proportional to time, then that does mean that doing an equal amount of work in a smaller amount of time actually increases the power. So in general, assuming this stays constant, making the time larger makes power lower, or making the time smaller makes power larger. So assuming you're doing equal amounts of work, the less time you spend on it, the more powerful you are. So let's do an example question. How much work can a 5,000 watt motor do in 10 seconds? If you label, this really helps. So we're looking for work, and they gave us 5,000 watts. That's a power, and the time is 10 seconds. So we can use our standard equation, I think, here, that says power is work over time, and we are looking for work, so we're going to isolate for that, and I'm getting W is PT. The power is 5,000 watts, and the time is 10 seconds, which means that the work done is 50,000. Of course, this is a very large number for the number of joules, so oftentimes you'll see this in scientific notation. 5.0 times 10 to the fourth joules should do the trick. Let's try another one. Determine the power, that's P, developed by a man weighing 6.0 by 10 to the 2 newtons. This is his force. If he climbs a rope at constant speed, at a speed of 2 meters per second. So there's my average speed. I think we're going to use one of the variations for power, which is P equals FV. It's on your reference table. I think it's the last relationship you'll see for power. But it's already set up the right way, so we just substitute and solve. The force is 600 newtons, and the average speed is 2, which means that the power he's developing is 1,200 watts. And with significant figures, I'm getting 698 watts. So for the second part of the question, when we're asked to solve for the total vertical displacement, I recommend this equation. Work is force times distance from previously in the lesson. And we're looking for the value d, so I will just rearrange, and it'll say that distance is work divided by force. So the work that he did was stated earlier in the question. It's 8.58 by 10 to the 3 joules. And the force is equal to his weight. So that's going to be 7.80 by 10 to the 2. So as you know, I like to do the coefficients separately from the exponents. So when I do 8.58 over 7.8, I get 1.09, and it's going to be times 10 to the something. And when I have 10 to the third divided by 10 to the 2, you subtract the 2 from the 3. So it'll be 10 to the 1. And this is proper scientific notation, but it's a bit awkward considering it's so low. So I would recommend just writing 10.9 meters as the distance that he climbed. Another sample problem. We have a horizontal force of 6 newtons to the left, and it's applied to a box on a counter to overcome friction. We want to calculate the power dissipated in moving the box 3 meters to the left along the counter in 1.5 seconds. So we have a force, a power, a distance, and a time. So on the reference table, we know that power is work over time, but we don't have a work. So going further from there, and also on your reference table, you can remember that work is force times distance. So if you do force and distance instead of work and put it over time, then we do, I think, have all the variables we would need to calculate the power. So I'll just plug in from here. And the force was stated as 6 newtons. The distance was stated as 3 meters. And the time was 1.5. So we have essentially 18 over 1.5, which is, of course, 12 watts of power that are being developed. Another sample problem. In raising an object vertically at a constant speed of 2 meters per second, so average speed, the power developed is 18 watts. So there's my power. Calculate the weight, which is Fg, or just a force. So we know that power is work over time, but we don't have a weight using that equation. We also know that work is force times distance over time, and we could think of the force as a weight, but we do not have a distance, nor do we have a time. So going further from there, distance over time can be thought of as average speed, so that means that power is also force times average speed. This is going to be the one that we're going to use, and we are calculating for F, so when I'm just going to rewrite this so that it's less confusing. We're solving for F, and I'm going to divide both sides by average speed, and that means that the force is going to be power divided by the average speed. The power was stated as 18 watts, and the average speed was 2 meters per second, and that means that the weight must be 9 newtons. And with that, we have reached our pair-up. So I will have these photocopied for you when you see me for class after this lesson. This will be on it as well. But I need you to copy these summary questions and put them underneath the Do Now on your separate classwork page. So on that separate classwork page, if I'm not mistaken, you just have the homework assignment listed, the aim, the Do Now, and this summary. Thanks for watching.